The Astronomy Club of University of Sri Jayawardenepura is proud to conduct a webinar for the year 2024 on the topic of Introduction to Gravitational Wave Astronomy. Initially, let me first of all welcome all of you who has joined here with us today, especially our senior treasurer of the Japura Astronomy Club, Professor Lilani resource person for the day, our club president, secretary, and all the individuals who has gathered here today. As you all already know, Japura Astronomy Club is always bringing you all something exciting. So, for those who are really eager to know about the mysteries of our universe, the fascinating world of black holes through the lens of gravitational waves represent space-time caused by accelerating massive objects, offer a revolutionary way to study black holes. They allow us to observe collisions and mergers of black holes, phenomena previously undetectable through traditional telescopes. These waves provide direct evidence of the dynamics in extreme gravity environments, enabling test of Einstein's general relativity. Here we have invited expert on the field. Let me have the honor to introduce our resource person for the day, Mrs.Purnima is a SEC Emergent Scholar Fellow. She is Ph.D. candidate, Gravity and Astrophysics Group, University of Mississippi. Madam, we really value your presence today with the Japura Astronomy Club, and we have arranged a small video clip on behalf of the club before the session. So let us have a look into it. Hope you will be happy. For being here today. We are thrilled to introduce our guest speaker. Let's all give a hearty welcome to our distinguished guest. Before moving on to the session, let me remind you thing. Chances are always rare, so once you see a chance, just grab it and get the maximum use of it. So, soon after the session, you may enter into an engaging Q&A session, either by unmuting yourselves or by dropping your questions in the chat box. So you never know the worth of moment unless you get the use of it. So make yourself comfortable. So without any further delay, let me invite Mrs. Purnima, our resource person for the day to take over. Over to you, madam.
Okay, good morning, good afternoon, good evening, all of you from wherever you're attending this webinar. I am hoping that you can hear me well and you can also see my introduction scene. Can someone confirm that you can hear and see things well?
Yes, madam, we can see you.
Okay, great. So I would like to start by thanking the Astro Club of Jaipur University for making this lovely introduction video and for putting all this together. It has been a wonderful experience working with you all. And I am really excited to take you all on this journey through discovering gravity's secrets and going through the world of black holes through detecting gravitational waves. With that, let me quickly show you the storyline that we have for you today. The storyline goes as follows. I would like to start by talking about giving you a little background on the evolution of gravity. That is, how gravity started with an idea and turned out into a theory. Then we would talk a little bit about understanding black holes, just the theory and astrophysical reasoning behind it. Then slowly move on to the concept or the theme of today's talk, which is gravitational waves, and how we detect these ripples in space-time. Then I'd move on to some cutting edge technology and state of the art facilities that we have today in order to detect these gravitational waves. And finally, I'll talk a little bit about my own research and how I contribute to this larger puzzle and some tips on how you all can get involved. So with that, let me begin. Okay, so gravity was not developed overnight. It has been a theory that has been with us for years and years. So it all started from Aristotle in 384 to 322 BC, who proposed that the Earth was the center of the universe. And this sort of a model is called a geocentric model. And his proposition was that the things that fall on Earth are falling in the center of the universe to their natural place. However, this was not completely true. And further, in 1600s and 1700s, Isaac Newton came up with this concept of Newton's theory of gravitation. And as we all know, the famous Newton and the apple incident. So he got this inspiration by watching an apple fall from a tree. And he wondered, is the same force that is helping the apple to fall from the tree on the ground is helping the earth to move around the sun and the moon to move around the earth. And that is how he defined gravity, like an instant force that helps to attract things one to another. However, there were some limitations to Newton's theory of gravitation, and his theory was not able to explain everything that we saw amongst ourselves in nature. And thus, we needed an updated theory, which is from our favorite Albert Einstein. And his theory is termed as the theory of general relativity. And he proposed that gravity is not just a force, but a curvature of space and time caused by mass. Well, what is space and time, and what is this curvature are we talking about? That is the theme for the first half of the talk. And the overall concept or the overall theory of gravity that we would be using in today's talk is that of Einstein's theory of general relativity. Because as of today, this is the theory that explains nature the best. So let me start by showing you a little animation of what Einstein postulated and what do you mean by the space-time mesh and the curvature of space-time. So here what you see is this large mesh and the horizontal and vertical lines here are made up of space and time. And he proposed that we are surrounded completely by the space-time mesh. And then when you have a massive object that is put into this mesh, it is going to produce a dip or a curve in the mesh. And then when you have a smaller body in this area of the curvature or area of the dip, it is naturally going to fall into this larger object. So Einstein's idea was that this is not like an instantaneous force that the Earth and Sun are experiencing or the Moon and Earth are experiencing. This is due to this large space-time mesh that is surrounding us and the curvature or the dip that is caused by matter moving in it. And as you can imagine from this diagram, the larger the curvature, the larger the mass of the body, the larger would be the dip. And if whenever you have a smaller body that's coming towards it, it's going to fall into this dip, and that falling into the dip is called gravity. That is, you're following the curvature that is created in the space-time. Then the next question is, so this is the underlying theme for today's talk, is that we have this space-time continuum, and Einstein's theory of gravity postulates gravity as a curvature of space-time. Then the second most interesting part of today's talk is that of black holes. So let me start by giving you a visual of what a black hole looks like, or how is it formed. I don't know if many of you know this, but black hole is actually a death star. Black hole is formed when a star is dead. So a star like our sun, it emits radiation or emits energy and light because of something that's fueling the sun from inside. But this is not something that's going to go on forever and ever, right? There is going to be some point when it is going to get exhausted of this fuel and die. And the death of the star is going to look something like this, which is a massive explosion called a supernova. And this explosion then creates a remnant in the center of the supernova. And now the star has become so dense that it cannot stay in its own gravity. And the gravity is pulling and pulling and compressing the star. And this final remnant after a supernova explosion is called a black hole, which is a highly compact and a highly dense and a highly gravitating object, which comes at the end of a star's life cycle. Then the question is, how did this theory of black holes even develop? And for that, we would like to talk about a list of scientists that contributed to this large puzzle. So the idea of black holes did not come overnight, right? There has been a grading or the gradation of thoughts over large and large periods of years. So this started from John Michell, who was the first person to postulate the idea that there could be something like a dark star, which is formed at the end of a star's life cycle. And this was in the 1700s. And following this, we have our very famous Einstein's equation, who created a mathematical framework to be able to explain gravity. And now that he provided us with this mathematical framework, we had a person named Carl Schwarzschild who gave us the first solution to Einstein's equation, which is a solution of a static black hole. And all this was happening in the 1900s. Following this, we have Subramanian Chandrasekhar, whose calculations helped us to model the life cycle or the dying cycle of a star, and at what point will a star turn into a black hole. And finally, it was John Wheeler who postulated this term called a black hole. Until then, it was just something called as a dark star. And it was until John Wheeler postulated this term called a black hole. And this is sort of now forming an entire puzzle. And these are just some of the people who have contributed to us understanding, or even the very little understanding that we have today about black holes. Then the question is, now that we are talking about Einstein's theory of gravity and have the framework of Einstein's theory of gravity, how does a black hole affect this space and time continuum? And that is happening like this. The black hole is so massive and so compact, and it has such a high gravity that it is creating this large curvature in space-time, which is infinite. And now you must have heard this popular term that anything that goes close to a black hole cannot escape it. That is because of this. Since the black hole creates this infinite curvature, anything that is coming close to this curvature has to fall into this dip, and it cannot escape the wrath of a black hole. And in terms of Einstein's theory of gravity, this is what a black hole space-time or a black hole dipped or a curved space-time would look like. And although this idea was developing from the 1700s to the 1900s, it was only in 2019 that we were able to first picture a black hole. It has taken us a really long time, and we have come a really long way from just ideating something like a dark star. We didn't even know if it was real. I mean, we can do some pen and paper math and pen and paper physics and come up with some theories and models. But until we make an observation, how do we even know if it's real? And here was the proof that all the theories about black holes are indeed real. And using the Event Horizon Telescope, we were able to first capture an image of this black hole in the center of our very own Milky Way galaxy. So now that I have given you an idea of what a black hole looks like, or how is a black hole formed, and how it curves the space-time, which is a part of Einstein's theory of gravity, the next question that we can ask is what happens when these black holes move in space and time? And this is when we would come to the second part of our talk, which is that of gravitational waves. And the effect that black holes have when they are moving in space-time is something very similar that all of you might have definitely seen at least once in your life, which is water flowing in a pond or water ripples in a pond. So when you throw a stone in a pond, you would see these ripples flowing away from the center. And this is exactly what is going to happen when you have black holes move in space-time. Why? Because space-time is this medium like water that is covering all of space. And now we have these black holes which are moving or revolving or doing some kind of accelerated motion. And this motion is going to disrupt the space-time continuum and going to give out some kind of ripples in the space-time. And these ripples are then called gravitational waves. For today's talk, the specific phenomena that we're going to look at is merging black holes. That is, if we have two black holes which are revolving around each other, and when they come and finally merge into one bigger black hole, what would happen? That is exactly shown in this illustration. Here, what you can see is in that smaller box to your bottom right, you see that two black holes are revolving around each other and they are giving out these ripples in space-time. And these ripples, which are the ripples of the space-time itself or ripples of gravity itself, are called gravitational waves. And now these two black holes have fallen into one another and caused a bigger black hole and giving out our signal. Now, in the horizontal axis, if you might have noticed, there is the wave-like nature. And this wave-like nature is the wave nature or the evolution of a gravitational wave. Then let us take a closer look into what exactly is happening. Now, the merger of a black hole or of binary black holes are coming in three regimes, which is in spiral, merger, and ring down. So the in spiral regime is the regime when you have these two black holes and they are circling around each other. And this is called inspiraling because they are spiraling towards one another. And then when they are close enough, they're going to come to a point when they are going to merge with one another. And finally, when they have merged into one bigger black hole, they are going to keep rotating until they settle down, which is called the ring down. And this gives us a very unique nature or a very specific evolution of a wave called as a gravitational wave, which is the signal that is shown below in red and blue. And this is the evolution of a gravitational wave strain or a gravitational wave signal, where it has this long inspiral regime, which is this long regime. And then you would see a sudden shift in the amplitude, which is the peak of the signal that happens when the merger of the black holes happen. And then when the ring down happens and when it starts cooling down, the wave again starts dying down in its amplitude. So now that we have theorized on what is happening when two black holes merge and how these ripples in space-time are given out and how these gravitational waves are produced, the next natural question is, what are the effects of these gravitational waves? Because if we don't know how these gravitational waves are going to affect us, how can we even detect them? So then let us do something. Let us construct our own space and time, which is shown as a grid here. And let us populate that with some particles which are forming a ring. So this is called a ring of particles. And as a gravitational wave is passing, you can see that the particles are moving in the vertical and the horizontal direction, which is called as a polarization or a plus polarization, because you see the particles moving in the vertical and the horizontal direction forming a plus. So this is one of the effect, which is stretching and compressing of space-time causing in this polarization. The second effect is what you see on the ring of particles, which is called a cross polarizations, because the particles are now going back and forth in a cross manner. So we have developed this idea that a passing gravitational wave will have two sorts of effects. One is plus polarization and a cross polarization, where the polarization term is a very fancy term to show the nature of how these particles are going to move, or how the space-time is going to let these particles move when a gravitational wave is passing. Now we understand how gravitational waves are going to affect bodies in general as they pass through it. And your next natural question may be, so does gravitational wave not pass through you and me? Of course, gravitational waves are passing through all of us and creating these vibrations or creating these deviations, but it's small enough. And how small enough, we'll see later. And now that we know here what is the sort of effect that gravitational waves cause in bodies, the next natural thing would be to check how, by keeping a detector, we can capture this radiation. So now what we can do is attach two bodies, and these two bodies will have this movement as and when the gravitational waves are going to pass by them. And this is the movement that we would want to detect. Okay, so now I would like to give you an idea of how large of a movement this is, or how small of a movement this is. And here I'm going to show you a video to show the smallness to the largeness of our universe. And here I'm going to use a term called a light year, where a light year is just a unit of distance. It is the distance the light travels in 1 year, which is approximately 9.46 trillion kilometers. And on the right-hand side, for those of you who are not familiar with how we denote the exponents, is a table of how large 10 to the power 18 is and how small 10 to the power minus 18 is. And thus, I'm going to start this video. Let me pause this video real quick. And here, what we are doing is we are starting from our Milky Way galaxy and then zooming in and in and in and going from a large structure to a small structure. And here, the numbers that you will see on the top of the video, like 20, 18, 15, are the exponent values. Here, 20 means the size of the Milky Way is 10 to the power 20 kilometers. And as and when we keep zooming in, this number is going to become smaller and smaller, and that is going to tell you the largeness or the smallness of the object that you see in front of you. So slowly we are moving into the Milky Way, where 10 to the power 16, 10 to the power 15 is around a light year. And finally we arrive at the big planet and go to our Earth. Now we are at the point of which can finding meters. Okay, so I just got to know that when the video is playing, you cannot hear me. So what I was trying to say is that here we are going from a large scale, which is from the scale of a Milky Way, to a really small scale. So you saw that we are zooming in from a Milky Way. We slowly entered our solar system. We slowly approached Earth. We went into a city. We saw humans. Then we saw a really small, tiny raindrop, zoomed into a raindrop, went to the level of our DNA, went into the level of molecules, and then an atom. And the final thing that you saw on the screen, which is of the order 10 to the power minus 15, was that of a nucleus. So let me play this again for you to compare what you can see on a large scale to what you can see on a small. Okay, so we went from 10 to the power 20, which is 1 and these many number of zeros, to 10 to the power minus 15, which is size of an atom. Now, then the question is, where in this spectrum does the deviation caused by a gravitational wave lie? Or how much is the change that is caused by gravitational wave? And that change is of the order 10 to the power minus 21, which is smaller than the size of an atom. And this is coming from black holes, which are merging a few billion light years away. So this is the deviation that we want or aiming to detect, right? And thankfully, we have been able to achieve it. So then the question is, how do we even detect such a small deviation? And for this, let me talk about the first detection, which was done in 2015. And if you remembered, the time when Einstein postulated the theory of gravity, the year was 1915. So gravitational waves are a consequence of Einstein's theory. And there has been a lot of resistance to this idea because it was bizarre to even think that a wave of gravity itself would exist. So it took us 100 years to come or develop the technology or to believe in Einstein's theory and to finally develop the technology to be able to detect these gravitational waves. And this is the detectors which first detected the gravitational waves in 2015 called LIGO. And you can see two detectors here, one in Livingston, one in Hanford in the USA. And here you can see that it has these arms, which are 4 kilometers each, and they are both placed at different locations separated by thousands of kilometers. So what next? Like, what is the technology that's going on inside this detector, and how are we detecting this deviation? And here is a zoomed in version of the LIGO site, where you can see these two very long 4-kilometer arms. And the way that is done is by placing large mirrors on the end of each arm and by shining a laser from the center of this facility into these two mirrors. And using a concept that we have learned in our undergrads, a very simple concept called as a Michelson interferometer. We are using a Michelson interferometer to detect a gravitational wave of the order 10 to the power minus 21 coming from merging black holes millions of light years away. So let me show you a little bit on how this technology is working. Now I have a laser, and for those of you who don't know how Michelson interferometer works, I am shining a laser that's split into these two arms, and the end of which I have two mirrors. Now, since they're going to go and hit the mirrors, they're going to be reflected back and come back at the beam splitter in some waveform pattern. And then we see something called as an interference of light. So the interference of light is that when you have two light waves, so now here we are talking about the light waves and not the gravitational waves. So when you have two light waves which are in line with each other, that means if the peak is aligned with the peak and the valley is aligned with the valley, you would have something called as a constructive interference, where the resultant wave is larger in amplitude. Whereas if you have the two waves which are out of phase, that is as shown in this diagram, which is the valley is in line with the peak, then you would have a destructive interference when there will be no light. So this is the concept that is being used to detect gravitational waves. So then when the gravitational wave detector is set in such a way that you would have zero interference at the screen. That is, the two lasers coming in destructively interfere and have zero brightness at the screen. And then when a gravitational wave is passing, the mirrors are going to move by 10 to the power minus 21 meter. And that movement is going to change the interference pattern that is seen on the screen. And by detecting this change in the interference pattern, we are going to have that frequency evolution of our gravitational wave. So we are using a very simple concept of laser interferometry, of using lasers and a Michelson interferometer to detect a deviation that is caused by gravitational wave. So then, now that I have given you bits and pieces of everything on how black holes merge, how it's distorting the space-time, how we have this large detector, and how we use the laser interferometer, now I'm going to show you a journey of a gravitational wave, starting from black holes to it being detected. So I hope you enjoy this journey.
This is the sound of two black holes colliding and merging. Where did this sound come from? A long time ago, in the distant reaches of the universe, two black holes, each about 30 times as massive as our Sun, were locked in orbit and spiraling in towards each other. The only visible traces of this spinning cataclysm would have been the way their gravitational fields warped the light of distant stars. Even as they collided and merged, there wasn't a flicker of light to be seen. The real and very violent action in this system was in the form of gravitational waves, ripples in the very fabric of space and time. These waves were constantly draining energy from the black hole orbits, leading to their ultimate collision and merger to form a single black hole. At that instant, the power of the gravitational waves was 50 times greater than that of all the stars in the universe combined. That pulse of gravitational waves, lasting only a fraction of a second, expanded through the universe, passing unimpeded through countless galaxies. About 1.3 billion years later, it reached Earth. Gravitational waves alternately stretch and squeeze space itself and everything they pass through, but the effect is minuscule. Their effect on Earth here has been vastly exaggerated to help visualize something that is otherwise invisible on this scale. To detect them and directly measure their properties, scientists built LIGO, the most sensitive measuring device ever made. LIGO uses a device known as an interferometer to measure the tiny displacements in space. In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along the 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.
Okay, so I hope you really enjoyed that journey because it's not something that happened over a night. It took years and years and years to come to this point to have finally detected a gravitational wave. Then the question is, now that we have the gravitational wave signal coming to us, how can we extract the information about black holes from these gravitational waves? And for that, we use a technique which is as follows. So in the blue here, you see a real gravitational wave data. And in the orange here is a model of an ideal gravitational wave that would be formed. And this model is created with a certain mass of a black hole and a certain distance to a black hole. Say, for example, the mass here is 200 times the mass of the sun, and it is 800 megaparsec, where megaparsec is just a unit of distance. So then we have a bunch of such templates for varying masses and varying distances. So when we have this real signal coming in, then what you would want to do is to vary your template. That is, now you're varying your distance and varying the mass to be able to change your wave nature and then overlap it with the signal that is incoming until to a point where it exactly matches the signal. And this matching between the data and the model is giving us the parameters of a black hole. And using this, we can get information about the distance of a black hole and the total mass of a black hole, the spin of the black hole, and so on and so forth. And all of this is encapsulated in a really interesting tool that is created by one of my colleagues, Akshay. And this is something that you can play around with as well, which is an interactive gravitational wave tool. You can go to interactivegw.com. And here what you see is that you have two black holes in space. And these are black holes that in space-time where you can move them. And on the left-hand side, you see a bunch of parameters. Now I'm going to change the mass of the black hole. So you can see that the black hole is becoming larger and larger. And as I change this mass, the wave on the top is also changing. Right? So that means today we exactly know what mass of a black hole is going to produce what sort of a wave, and that is going to help us build these models using which we can extract data about or extract parameters of black holes. So now that we are done with getting information from gravitational waves, decoding black holes, and constructing a detector, what's next? So there have been other detectors which are built in other parts of the world. LIGO is in the US. Similarly, we have Virgo, which is in Europe, which has these 3-kilometer arms. And then there is Kagra, which is built underground. And you may ask why underground? And one of the basic reason or one of the most important reason is that you would want to avoid seismic activity. Since our detectors are so sensitive, they would detect anything from a falling leaf from a tree to an earthquake. And in order to avoid these noises on Earth, they are building an underground interferometer. And thus, you can see that you have these interferometers in different parts of the world, and detecting or the gravitational wave astrophysics is more or less a collaboration which is among different countries in the world. So it's like a global or an international collaboration where you have these ground-based detectors in the US, Europe, Japan, and one soon coming up in India. Then the question is, what's next? What is the future of gravitational wave astronomy? And the future is building more detectors and more sensitive detectors to get more information from black holes. And one of the future detectors is called the Einstein telescope, where here you can see are just two versions of this underground interferometer, which now has the shape of a triangle. Because now you don't need two L-shaped detectors, right? You can have a triangle and create your own pairs. And this is going to be underground, again, to protect us from all the noise on Earth. And it's going to be built in the borders of Netherlands, Belgium, and Germany. The other detector that's coming up is called Cosmic Explorer. And now you can see how large the arms of this is going to be. LIGO had arms of 4 kilometers, and now the Cosmic Explorer is going to have two facilities with arms 20 kilometers and 40 kilometers. So you can imagine how large this structure would be. Then the question is, why? Why do we invest so much money in building these detectors if we already have gravitational waves that we have detected? And that is because we want to cover the entire universe. So what you can see in this figure here is in yellows are two stars which are colliding. So far we have only talked about gravitational waves from two black holes in spiraling. This could also happen when there are two massive stars which are in spiraling. And in yellow, we have stars. In white, we have this binary black hole merger. And on the axis on top, you can see how far away in the universe are we going. So it starts from 1 billion years to 4 to 7 to 10 to 13 billion years. And thus, with the future detectors like Cosmic Explorer and Einstein Telescope, we would be able to detect 99% or more of these inspiraling objects. Isn't that amazing that we will be able to see all of the merging binaries there? So then the question is, why? Okay, one thing about building these multiple detectors is to cover the universe. The other reason why we want to do so is to look at other sources that are producing gravitational waves. And that could be either a supernova explosion, which is one of the brightest explosion that happens in nature. It could be from two neutron stars, which are disrupting the space-time curve and creating gravitational waves. It could be from a pulsar. And each of these sources are going to produce gravitational waves at different scales. So just like you have your electromagnetic spectrum, where you have X-rays, microwaves, visible light, radio waves, and so on, the same way there are different frequencies or time scales for these gravitational waves coming from different sources. And the ground-based detectors that we have so far are only limited to a certain frequency range that will only cover a certain set of astrophysical sources. In order to expand our view, we have to go one step further, which is called a space-based observatory, which is one of the coolest things that coolest videos that I have seen, because it's crazy to see that you have 3 mirrors now in space, and they are going to be shining laser from one to another to detect the interference pattern due to a passing gravitational wave. And here, let me show you a quick video of that. Okay, so I'm going to mute the volume here and talk a little bit about what's going on. So these are 3 mirrors that are in space, which are shining laser to each other and calibrating them and adjusting where they should be. So before I show, any guesses on how long these arms are? Okay, let's see if you can find now. So this is our Earth, this is our solar system, and you can see Jupiter and Saturn and the Sun. And this is going to be the arm of our interferometer, which is going across our solar system of the length of 5 million kilometers. And this system is going to be revolving around the Sun along with Earth. And such a big space interferometer is again going to detect gravitational waves. So my mind was blown away when I saw this video of LISA, which is the space-based interferometer, which is the next step where we are going with our gravitational wave detection. And all of these future detectors are going to come up in the next 15 to 20 years. So that gives you all enough time, since I know that a lot of you are doing undergrad physics, to be a part of these collaborations and work with one of such collaborations. So now humans are not satisfied with just having an interferometer in space. So what is one step further? And the one step further is to have a detector on the moon, which is a proposal called the Lunar Gravitational Wave Antenna, where they want to measure the vibrations of the moon caused by gravitational waves. This is just a proposal, and it's still yet to go in the, it's still yet to be sanctioned and yet to get funding to see if this is actually possible. So as you can see, the possibilities are infinite. There is no stopping us. from the first detection of gravitational wave that happened in 2015, that was just the first step. We are in an era where we are having rich gravitational wave signals, and from now on, it's just going to grow and grow and grow. So with that, let me talk a little bit about my current research and how I am involved in this larger picture of gravitational wave astronomy. And the research that I do is testing general relativity or testing Einstein's theory of gravity. So, as you all know, getting information from black holes is not easy, and black holes are one of the most mysterious objects. So now that we are receiving these gravitational waves from black holes, it's opening a window to a new regime or a new side of the universe where Einstein's theory has not been tested. So it's still called a theory because we don't know if it's going to explain everything. We today know that there are some things like dark energy and dark matter that are not being explained by Einstein's theory. So we don't know if this is the ultimate theory or if there is a larger theory that is going to help us describe the nature or describe the universe better. So thus, my work is to test Einstein's theory in the regimes of merging black holes. Because this theory is well tested within our solar system, Einstein's theory exactly tells us how the planets move with high accuracy. However, it has not yet been tested in regions like binary black holes. And thus, my work is to use gravitational waves as a tool to test Einstein's theory in such regions and see if these objects also follow Einstein's theory of general relativity. And as a part of my work, my collaboration, I'm a part of the LISA consortium. I'm part of the LIGO and the LIGO Virgo Kaga consortium. And this is my advisor, Dr. Anuradha Gupta, and the postdoc, Dr. Nathan Johnson McDaniel, along with whom I've been working here at the University of Mississippi. And here is a QR code of the paper that we put out last year, which is along the lines of testing Einstein's theory of general relativity with gravitational waves. So you can check it out if it interests you. So then now I've talked about my journey and all the gravitational wave physics and all the nice things. Then the natural next question is, how can you get involved? Or on whatever levels you are, how can you participate in gravitational wave astronomy? And for that, I have some tips that I have received or that I have put together from the lessons I have learned from my own journey. And the first things is to indulge in computer programming, because learning computer programming today is being used everywhere, and especially in the kind of physics or the kind of work that we do in gravitational wave astronomy includes a lot of computer programming. Then look for summer and winter schools on the areas of your interest. So different countries and different research institutes have put out the summer and winter schools on introduction to gravitational wave astronomy, introduction to black holes, introduction to radio astronomy. So just keep an eye out for all these different summer schools where you can get a flavor of how things are going on and you can do some hands-on research. The third thing is to check out some public outreach or citizen science program, which one of the LIGOs is called Gravity Spy. So this is something that if you just Google LIGO Gravity Spy, this will give you, as a layman or as any citizen who does not know anything about physics or astronomy, to go and work with real gravitational wave data and to play around with that data. So please make use of this. And finally, don't shy away from asking questions or contacting people. In general, the people in the physics or science community are friendly and they would like to see the interest coming from general audience or younger audience, because there are so many projects lined up. As you saw, the future of gravitational wave astronomy is really bright and it could use a lot of help from all of you. So please don't feel shy to ask any questions after this talk or to contact me or anyone that you see is interesting. With that, I'd like to finally acknowledge some of the people because of whom this could happen, which is my husband, Maha here, who is an alumni of Japura Physics. And a conversation between him and Lilani ma'am resulted in this idea of me giving this webinar. So thank you, you too. And finally, last but not the least, to Japura Astronomy Club. I think you all have done a wonderful job in organizing this and making this happen. So thank you so much. With that, I'd like to conclude my talk and leave my email ID and a QR code to my webpage, which you're free to visit and free to contact me further. And I hope that all of you, regardless of what background you're coming from, could take away something from this talk. So thank you.
The session time is up. Feel free to reach out to us via our social media links. You can send us your questions and we'll make sure to pass them along to the resource person to get you the answers you need.
Okay, I do see some questions in the chat. Oh. Okay, thank you. I don't see any questions yet. Yeah, so feel free to ask, raise your hand and ask a question, or just type your question in the chat. Yes, so LISA is a future project and it's supposed to come up by 2035, but it could go up to 2040. So the next 15 years. I see a question on the requirements for admission of a PhD program at the University of Mississippi. So yes, I think it's better that you contact me separately for that, and we could have a chat about that. It's the same. You go through your GRE, you put together all your CV and your recommendation letters and fill in the application. But we could talk about this in detail over email, or maybe we could set up a meeting for that. Okay, there's a question saying, would you like to brief us about the ripples in the form of gravitational waves? Yes, so the ripples are the ripples of space-time itself. And these ripples are called gravitational waves. As I talked about in the beginning, it's like throwing a stone in a pond. And as you see these water waves going, it's the ripples of the space-time which result in gravitational waves. I hope that answers your question. Okay, next question is, how can we enter the astronomy field from a bachelor degree? So it depends, a bachelor degree in what? So my path has been that I did a bachelor's in physics, and then I did my master's in astrophysics, and now I'm doing a PhD in physics. So there are options for doing a master's in physics or astrophysics as well, and directly to come into a PhD program from your bachelor's. So both these options are available. And if you are doing a 4-year bachelor program, you can make a switch and apply for graduate schools all across the world. And that way you can enter into it. But if you think that you need some foundation of astronomy or astrophysics, then you can apply for a master's in astrophysics program and get some idea or foundation in astrophysics and then apply for a PhD program. Okay, yes, what is the question?
Yeah, so can you hear me?
Yes, I can.
Yeah. Thanks for this amazing lecture. It was the dedication of you on this subject was truly contagious, and it has sucked me in just like a black hole and wouldn't let me go out of it. Thank you so much. My question is, are there any potential risks or any unforeseen dangers of unlocking these new secrets of the universe or the black holes?
So as I told you how far these black holes are from us, These are billions of kilometers away from us. So unless you travel close to a black hole, you are not going to have any harm effects from a black hole. What you're all doing is sitting on a small planet like Earth, doing a little bit of physics and maths and computational analysis, and finding out what's out there in the universe, which is billions and billions of kilometers away. So no, you don't have any harm from there. And we are not going to crash into a black hole anytime soon.
Okay, thank you.
Okay, I have a very interesting question. What are the potential applications or technologies derived from gravitational wave research that might impact other scientific or technological fields? That is a great question, Gayatri. So the technology that's been used in LIGO and other gravitational wave interferometers is cutting edge, and it's really state of the art. So this is something that not only physics people work towards. It's a collaboration between engineers, designers, physicists, electrical engineers, and mathematicians. So all of them have to come together and do this. And now, for example, the kind of conditions that you create in this detector are you have to make a very precise measurement, right? For that, first thing, you have to develop technologies to remove all the noise sources. Second, you have to develop technology to create vacuum in your arms. Third, you have to build really powerful lasers. And fourth, you have to develop a lot of scientific and statistical techniques to be able to analyze the gravitational wave data. So each of them have applications in other technological fields. Say, for example, they're creating this really large power laser, right? So that laser can be used for other studies as well, or the knowledge of how to create such a powerful laser can be used elsewhere. And as a gravitational wave community, we keep developing a lot of statistical analysis techniques. And these techniques do not have to be only applied to gravitational wave physics. They can be applied to general data science fields as well. And that is why a lot of people who do master's or Ph.D. in physics find jobs in corporate world, because the techniques or technology that they are working with here can be easily applied to other areas as well. Okay, interesting question. Can gravitational waves be somehow explained by Newtonian theory of gravity? That's a great question. So unfortunately, gravitational waves cannot be explained by the original theory that Newton postulated, because the Newton's idea of gravity is very different from Einstein's idea of gravity. Because according to Newton, gravity is an instantaneous force. That is, if I have a sun and earth here, if the sun collapses right now, I would instantly feel the force from the sun that the sun has collapsed. That is, there is no medium that between the sun and earth. There is no way how it can travel. But Einstein's theory of gravity gives room to this kind of a assumption, or this kind of a study, where if the sun is going to collapse right now, it would take us about 8 minutes to realize that the sun is collapsed. That means it is taking some time for the information to reach from one point to another. And that is because of these space-time distortions that are moving towards us. So Newton's theory cannot explain gravitational waves, but there has been a lot of research in modifying Newton's theory. So Einstein's theory is one theory. There is a separate set of people who are working on how can you change something within the Newtonian theory to explain all this. And that may or may not be able to explain gravitational waves. And that is also a large area of research now. Okay. You had mentioned that different sources of gravitational waves emit at different frequencies. How do you distinguish between them to identify what exactly the source is? That's a great question, Arvind. So as physicists, we work with a bunch of mathematical models. right? So we know astrophysically what happens when you have a supernova explosion. What happens when you have a neutron star binary? What happens when you have a black hole binary? So we can create models of how the gravitational waves look like in each of this scenario, and mathematically or computationally come to a point to check in what regime are these sources going to emit gravitational waves. And based on our astrophysical studies and computational techniques, we have exactly figured out that supernova explosion would give out gravitational waves in this frequency, whereas black holes will give it in a different frequency. So that's how you can distinguish between what frequency it is. Okay, next question is, what inspired you to pursue a career in gravitational wave astronomy? Okay, so believe it or not, the idea of wanting to do something with astronomy started when I attended a public talk on black holes, which was when I was in 8th grade or something in school. So my father used to take me to a lot of open science talks or open public talks. And that was the first time when I heard about black holes in general. Of course, there was no gravitational waves back then, but that sort of like sparked that curiosity in me of wanting to learn more about the night sky or space in general, because there are so many mysteries there. But then when I was doing my bachelor's, that is when the first detection of gravitational wave happened. And so our institute had some responsibility of creating some posters and doing some public outreach for gravitational wave astronomy. And that is when I learned about this area. And it's really exciting to me to think that there is a small theory that you can just do it on a computer or a pen or paper. And that theory exactly explains what is happening billions of years ago. So just that thought of having so much potential to understand what's going on and to solve the problems or mysteries is what inspired me to do a career in gravitational wave astronomy. Okay, next question. Do we have a relation between quantum physics and gravitational waves? Okay, great question. So one of the leading challenges that we have today in science or physics itself is to find an ultimate theory of everything, right? And that means you would want a theory that is explaining all that you observe in the quantum physics and all that you observe in larger gravitational physics. So far, we have not yet come across a theory that explains quantum theory and gravitation theory. So it is an open area of research to come up with this theory which can explain quantum physics and gravitational physics. But on the other side, when we talk about gravitational wave detection, right, we talk about lasers, and laser is light, and light is made up of photons. So then there is a field called where you can put your knowledge about quantum physics in order to figure out how accurately can I have my laser, or what are the sort of disadvantages if I use this sort of a laser. What are some quantum noises that are generating using this lasers? So that is one area where you can apply your knowledge about quantum physics. Okay, another question is, what is the unit of measurement of these waves, and how do you distinguish a gravitational wave from other kinds of wave emitted by different sources? Again, great question. So the unit of gravitational wave, so when you look at this gravitational wave nature, we call that as a strain, and that is a dimensionless unit, because that is just some sort of displacement that is caused in the space itself, and that does not have a unit. It's a dimensionless quantity. And the way we can differentiate gravitational waves from other sources is by looking at the evolution. Say, for example, we have data coming from seismic waves. We have data coming from some sort of windmill that's going on somewhere. But the gravitational waves have a very signature frequency evolution. Like you will have some in spiral regime, then you'll go at a chirp, at a peak, and then it will die down. And this signature signal is very difficult to be imitated by other sources. So we look for this signature signal, and that is how we can look at the frequency evolution and differentiate between gravitational waves and just other waves in nature. Okay, next question is there a limit up to how far in space gravitational waves can be detected? If so, does LISA mission plan to do so? So as far as I know, there should not be any limits to find how far of a gravitational wave you can detect. It's just about building a detector that would get information from farther sources. So there are a different set of study which look at cosmological sources of gravitational waves. That means sources that are really, really far away and that are coming from the Big Bang itself, right? So there is a different area which I did not talk about in my talk, which talks about this. And for that, we use something called as a pulsar timing array. It's not, I don't think LISA is going to do that. It's the job of pulsar timing array who's going to look at these cosmological sources. So maybe you would want to check that out. Okay, next question is, do you also calculate what frequency reaches Earth? Does the frequency change with distance? Okay, great question. So we are not looking at just the frequency, but how the frequency evolves in time. So let me take you to the gravitational wave signal. Right here. So what you see here is that in the beginning, we have a smaller frequency. And as we keep moving close to the merger and ring down, the frequency starts becoming larger and larger. So what we are sensitive to is that the evolution of this frequency. And the gravitational waves do not interact with matter as light would interact. So it can travel through different matters as well. And there is a field that looks into what if gravitational wave is deviated from something in between? What if it interacts with something in between and changes its frequency evolution? So yes, there could be some effects. There could be some effects on the frequency evolution. And that is also one of the things that I am looking at. But on a larger scale, or if you look at the percentage or the proportion of the ones that are changed and not changed, it's a larger portion that is coming unchanged. But there is a small possibility that it can have some interactions on its way before reaching us. Yes, it's a great line of thought. Okay, great. Thank you. Thank you. I hope you guys enjoyed it. And I hope you guys keep having more questions and feel free to email me with your questions. And I hope I was able to answer all your questions. Do we have any more questions? I don't see any more in the chat. Thank you. Any feedback form? I think that's a question for the organizers, if you have any way that the audience can give you a feedback. Thank you. Okay, I guess I don't see any more questions.
As we are running out of time, we have to end our Q&A session. So if you have further clarification, please feel free to join us through our social media. We will help to you all to get the answers back. So as we have to the end of another wonderful webinar, I would like to take the honor to thank each and everyone who gathered here today with us, even in your busy schedules. Specifically, I would like to thank our resources person for the day, Mrs.Purnima N Mahanama, for accepting our invitation and giving us a great opportunity to learn something really exciting and new for us. Also, I would to extend my heartiest thanks to our pillar of support, Professor Lilani Artigala, who is our senior club treasurer and also professor at Department of Physics at University of Sri Jayawardenepura. She has always stood behind us and guided us toward the success and helped us to fulfill our goals. Madam, we really value your guidance toward us. Also, a very big thank you for each and everyone who has been behind the screen and given the club a huge support, even in a manner. Thank you. We are forever grateful. No matter who you are and where you stand, you can always dream big and reach the unknown. Be happy with yourself because self-satisfaction matters the most. Cheers and have a great time.